Hello friends, in this session we will be dealing with diagonal canonical form. Let's begin. Yes, so far we have seen two types of canonical forms, right? One is CCF and the other one is OCF, right? We have seen them, and we have seen that yes, these two are applicable when your transfer function which is there t of s, it is in some fashion like this, that b naught into s power n plus b1 into s power n minus 1, and let us say at the end you have bn, right? Divided by if you think of s power n plus a1 into s power n minus 1 plus a2 into s power n minus 2, and this goes up to an, right? Fantastic. So yes, yes, we have said that yes, whenever our denominator, if it is in terms of polynomial of s, right, then in such a case we use CCF and OCF, and even there we have seen that we need to only focus on CCF, and OCF can be easily transformed, right? Because yes, we know that yes, AOCF is equal to ACCF transpose. Then we know that yes, B of BOCF is nothing but CCCF transpose. COCF is nothing but OBC, and so on and so forth, right? Yes, this was BCCF transpose, and this D was equal to D, right? We have seen that. So yes, but now what if you have the same numerator? You have the same numerator. I mean to say this one. If you have the transfer function in this fashion, that t of s is equal to, this numerator remains same, right? And just I change the denominator. Rather than this one, if I have the denominator in the forms of factors, I mean to say s plus 1 or s plus 2, and stuff like that. This is not plus, I'm so sorry. Multiplication, right? Yes. P2 multiplication on the s plus pn, right? So what if I have transfer function in this manner? How to show that? So yes, some people may say that, sir, what you can do is, you can just simply expand this term, expand this, and you can do that. Yes, agreed, no problem, right? But just imagine you can do that when you have 2 poles, 3 poles, 4 poles, 5 poles. What if you have 18 poles, 20 poles, 200 poles, 1000 poles? You just cannot do that, right? That is the reason that is not a way out. So we have two other different forms. Now you may ask me, sir, why you have two different forms of equations? See here, the two forms of state space model that we have, the first one is going to be, first one that we have is diagonal canonical form, and the other one that we are going to use is Jordan's canonical form. Don't worry, I will tell you what it is. See here, when I'm talking about diagonal canonical form, in the sense, do you agree that all of these it are the poles, right? They're the poles. Yes, you are right, sir. If the poles are distinct, then in that case, distinct in the sense poles are different, then in that case we are going to use this diagonal canonical form. Whereas when the poles are repeated, when you have repeated poles, then in such a case we are going to use Jordan's canonical form, right? Because we know that yes, we have seen that, because even in our stuff we have seen that, even in our transfer function approach we have seen that yes, there can be either distinct poles, and yes, definitely there can be repeated poles as well. So we need to think of distinct as well as repeated. So if at all we have a transfer function which has distinct poles, then in that case diagonal canonical form is used. And if you have repeated poles, then in such a case Jordan's canonical form is used. Now let us speak about diagonal canonical form. So in this case the transfer function that we are going to have is this way. We have already talked about it, right? The transfer function that we have is just going to be, and yes, this is also called as DCF. And let me write down that this is applicable when poles are distinct. Poles are distinct. This is very important. In the sense all P1, P2, P3, Pn all are different. So now let us think of this one. See, so this is applicable for a transfer function having T of s equal to, right? Yes. Now you please tell me, yes, see here, if you just think of here also we are thinking about n poles, and in the numerator also we are going to have n order, which means that it is a proper transfer function. So yes, as usual we are going to take the worst case scenario, that is proper transfer function case. Yes. Now what we have to do here, in order to make it in a diagonal canonical form, we have to represent it in terms of partial fractions. In terms of partial fractions. Now, but since it is a proper transfer function, means the degree of numerator and the degree of denominator are same, the first thing which we have to do is we need to divide the numerator by the denominator. Means first step is numerator upon denominator, divide them, and then form the partial fractions, right? So if you do that, then what you get is you get T of s equal to, because see, when you are dividing this stuff, then yes, definitely this b naught only will be there, which will be remaining. So you are going to have this b naught plus, now this is very important, this is very important, see here, you will have all the poles written here. Yes, s plus p1 plus, yes, s plus p2, and so on up to s plus pn, right? And if you know that, yes, you have already studied in your school days that here you always have this a, b and c. Here you have a, here you have b, and you have c, stuff like that, right? But I will be considering the same constant but by some another name, meaning that let me consider here c1, c2 and c3. Why c1, c2, c3 you will understand, don't worry, don't worry, it is going to be very very simple. So let me know. Now if you see here, yes, what are the c1, c2, and yes, this is not c3, this has to be cn, right? This has to be cn because it is for pn. So it is, so from c1, c2 up to cn, what we have is partial fraction constants. We call them as partial fraction constants, right? And yes, what are p1, p2, pn? P1, P2, Pn, what are they? They are nothing but the poles. Now here is the concept. See here. In your school days, you must have studied that whenever in the denominator you have a non-factorizable quadratic equation. Non-factorizable quadratic equation, let me take an example. For example, s squared plus 4, right? So in such a case, teacher says that in order to represent this in terms of a partial fraction, you have to take it as as plus b. Am I right? This you used to do in school, right? But then you need to understand one thing, that why I have not taken such a kind of consideration here in our equation. Why? Because when you were in school, you were expected that the answer that comes has to be real. I will tell you, see here, when you just equate this to 0, s squared plus 4 equal to 0, what do you get? You get s is equal to, s squared is equal to minus 4, so s is equal to plus minus j2. Am I right? Yes. So in school days, you were not at all introduced to something called as complex numbers or imaginary numbers and all, right? So, and the another fact is this we are dealing only in case of real. But in our control systems, if you see, we can have poles which are real and which are complex and which are imaginary as well, right? So that is the reason here we do not have the problem that we need to only have the roots real. We can also have complex roots, we can also have imaginary roots, right? So in our case, this as plus b concept will not be applicable because we are not expecting that the poles have to be real. We are not at all expecting it. Even it is imaginary, it is okay. Even if it is complex, it is okay. Doesn't care to me, right? So these are the few things. So yes, definitely as plus b concept will not be applicable in our this transfer function. Are you getting my point? Yes. Now see here how to write the diagonal canonical form for this transfer function. Let us see. For that, let me write the transfer function again in the partial fraction form. See, if I think of transfer function is t of s, let me write it in the form of partial fraction. Partial fraction is what? Yes, we have just done this, right? B0 and this stuff, right? So let me just write it down. B0 plus C1 upon S plus P1 plus C2 upon S plus P2, and the story completes at Cn upon S plus Pn. Am I right? Yes, definitely. Now what will be matrix A, matrix B, matrix C, and matrix D? That is the question. So it is very simple. It is very simple. Do you agree with me that we are only talking about diagonal canonical form? Yes. The moment we are talking about diagonal canonical form, it means that matrix A has to be diagonal. Why? Because if you see in the whole state space thing, only A matrix is a square matrix, right? So yes, definitely when we are talking about diagonal, because see, always you have diagonal for square matrices only, and only A matrix is the square matrix here. So yes, definitely this is going to be A. So how we will show that? Yes, so see here, this is very simple. You don't need to worry anything. See what you have to do. You please put these poles in the diagonal elements, because this A has to be a diagonal matrix. That's it. A is a diagonal matrix. What do we mean by diagonal matrix? Diagonal matrix indicates that diagonal elements are present and off diagonal elements are not present. Means off diagonal elements are zero. Right. So what will be those diagonal elements that we need to understand? Those diagonal elements will be nothing but the poles. So now, shouldn't may say that yes sir, if you are thinking about this, p1 is a pole, p2 is a pole, pn is a pole, let us just replace them, p1 p2 p3 in the diagonal form, and at the end we are going to have pn. Is it right? No, it is not right. Why? Because you don't get s plus 1 is the pole, because when it will become pole, when you equate s plus p1 to 0. This is a characteristic equation. So the moment you put s plus p1 equal to 0, you get s is equal to minus p1. Similarly, when you put s plus p2 equal to 0, you get s is equal to minus p2. Right. Similarly, when you put s plus pn equal to 0, you get s is equal to minus pn. So definitely these are not the poles. P1, P2, P3, Pn are not the poles. Rather, minus P1, minus P2, minus P3, minus Pn, they are the poles. I hope you are getting the point. Am I right? Yes. Now, what about other elements? Other off diagonal elements will be 0. Right? Yes? Yes. Now, what about B matrix? B matrix is very simple. B matrix is very simple. All are 1. All are 1. B matrix is very simple. In case of diagonal canonical form, B matrix is going to be all are going to be 1. Yes. So now what about C matrix, sir? Yes. C matrix, if you see, C matrix. In this C matrix, what you have is you are going to have these partial fraction constants. partial fraction constants, means this C1, C2 up to Cn. So here I am going to have C1, C2, C3, Cn. Now here is the concept. See here, if in A matrix I have written minus P1 first, then I have to write C1 first here, means whatever is there on the top of the pole you have to write it in the same order, which means order is very important. Now you may ask me, sir, why? Because for example, you have a friend, right? You are trying to solve a particular transfer function, you try to find this partial fraction form, right? Yes, in partial fraction form you may take that c1 upon s plus p1 first, and you may take c2 upon s plus p2 next. But it may happen that, because see, at the end of the day, this c1 and p1, they are constants only, right? So let me consider that this is 2, this is 5, let me consider this is 3, and this is 7. Now your friend solved it 3 upon s plus 7 first, and then he did 2 upon s plus 5, and he added them. Both are correct, both are correct. Then what is right? This is right that if you put minus 5 first, then you have to keep in the C matrix 2 first. Means if you keep here minus 5, then you have to keep minus 2 here. Very simple, right? Similarly, if you keep minus 7 here, this is 7, right? Minus 7 here, then you may need to keep 3 here. Now what about your friend? Your friend, he will come, he will say, yes, I have taken this first, I have taken this next. So he will take here minus 3, sorry, here he will take minus 7. So on top of minus 7 what we have is 3, so he will take 3 here. And he may take minus 5 second, he may take here as minus 5, and here he may write 2. So in such a cases both are correct. Just the thing is that the order has to be maintained. Order has to be maintained. If you take P1 first, then whatever is there on top of P1 you please take here in C1. Whatever is there on top of P2 you please take here in C2. Whatever is there on top of P3 you please take here. That's it. That is the only concept. So here order is important, right? Yes. Now let us think of D matrix. D matrix, as usual, it is going to be P naught, right? Yes. So this is the diagonal canonical form in general. What is there? It is going to be very simple. See, what you have to do is you just need to put the poles as the diagonal elements of the system matrix A. Then in your B matrix, all are ones. Yes. In your C matrix, your partial fraction coefficients will come, and those coefficients will be written in the same order of the poles. Same order of the poles. And matrix D is definitely, it is going to be B naught. Now see here, what are the important points you need to observe, because why this particular diagonal form is important, right? So it is important because see here, the moment we bring transfer function or the system in the diagonal canonical form, we can see whether the system is stable or unstable very easily just by observing this matrix A. Getting my point? Just by observing this matrix A, you will understand why. How? Because you can see these poles. Yes, you can see these poles directly. So just by looking at this matrix A, just by observing this, you can comment on the stability, whether it is stable or unstable. Right? Now, another fact is, for example, see here, I have any of the diagonal elements A as positive. A as positive means if this is A matrix, let us say, and you have, let us say, this is 1 0 0, let me 0 1 0, let me consider 0 minus 2 minus 1. Yes, let me consider this as 3. So if you see here, by this particular rule, minus p1 minus p2 minus p3 means these have to be negative, right? All have to be negative. But this 1, it is positive, this is positive, this 3 which is there, it is positive, this 3 is positive. What does that indicate? S is equal to 3, which means s minus 3 is equal to 0. Now s is equal to 3 indicates that pole is on the right half of the s plane. The moment pole is on the right, this is sigma, this is j omega, so pole is on the right half of the s plane, which means it is unstable. Getting my point, right? So just by looking at the system matrix in the diagonal form, we can understand that the system is stable or unstable. We can talk about that, right? Anyways, another point which is important is that if matrix A is singular, let me tell you. See, you please tell me, what is determinant of a diagonal matrix? Determinant of a diagonal matrix, is it multiplication of all the diagonal elements, right? Means if I somehow find the determinant of A, and if the determinant of A comes out to be 0, I may call it as a singular matrix, right? Yes, because whenever determinant of any matrix is 0, we call that matrix as a singular matrix, right? So if mod of A is equal to 0, which means, you please tell me, if this is equal to 0, what can happen? Means at least one of these poles, means out of this p1 p2 p3 pn, one of these pole has to be 0. At least one of the pole has to be 0. Means if the determinant of A which is there, if it is equal to 0, then it means that at least one pole is 0, or we can say one pole lies at origin, right? The moment one pole is there at origin, we say that system is marginally or critically stable, or critically stable, right? But I am saying at least one pole. No, it may happen that two poles are at origin. Yes, two poles are at origin. It may happen because, see here, you may consider, see, you may consider that. Let me consider, for example, minus 2 0 0 0 0 3 0 and 0 0 1, for example. So in this part and this minus 1, right? So here we have seen that this is negative, this is negative, no problem, all are good. But this is 0, right? So out of these three poles, 1 2 3, let me take another color. Out of these three poles, one is 0. Get my point? Out of these three poles, 1 2 and 3, this one is 0. The moment this one is 0, what does that mean? That one pole is 0, which means one pole is at origin. If I say that one pole is at origin, it means that it is a one pole is at origin, it means that it is marginally or critically stable, which is right. But it may happen, no, that this is also 0 and this is also 0. It may happen this is also 0, this is also 0. The moment both the poles are 0, which means that there are two poles at origin. Two poles at origin, which means it is going to be unstable. We have seen that. Repeated poles at origin will cause the system to be unstable. We know that, right? So because, see, when you have this repeated poles here, 1 upon s squared, what is 1 upon s squared? T squared. T, right? It is t. So t is always this way, impulse response. So that is the way you can understand that yes, it is going to be unstable, because with time it is increasing and it is reaching infinity, right? So this is the whole thing, right? Now see here, so these are the things which we can talk of, right? So the thing is that with a diagonal form, we can easily define the characteristics of the system, because just by looking at this matrix A, we were able to find out what, we were able to tell that the system is stable or unstable, right? So this is what is about the diagonal form. So this is all about the diagonal form. Thank you.